Let's go over serial communication. Now, at the beginning of the module, we explored what serial communication was. That is, it is a series of ones or zeros communicated over a wire. But we need to look at the finer details of serial communication. We can send serial data in two ways. We can use three wires, one for ground reference, another for a clock to synchronize the communication with both ends, and the third wire to transmit the data. Now, this is called synchronous serial communication because the two ends are synchronized by that shared clock pulse on the clock line. To save on wires, however, or in cases like wireless communication where we don't have that option of that third clock wire, we can communicate using only two wires or a single radio frequency. So we ditch the synchronizing clock signal. So this just means we have to take some extra steps so that the receiver knows exactly when the sender is sending either a 0 or a 1. We call this asynchronous serial communication because it is without synchronization. Asynchronous tends to be far more common than synchronous, especially where wireless digital communication has become the norm. Bluetooth, Wi-Fi, cellular service, etc. So you're going to need to send 1 byte of data over a serial link. You can send it one of two ways. You can send it the least significant bit first or the most significant bit first. Doesn't matter, your choice. But you obviously need to make this decision before you attempt communication. Sending the data least significant bit first is sending the little number end of the byte first, right? So we call this communication little endian. If we send it the most significant bit first, we call it the big endian because we're sending the big end number first. The most common method, or the most common way, is little endian, or least significant bit first. Once you've decided which bits you're sending first, you then need to decide how fast you want to send those bits. How many bits per second? This is called the baud rate. The most common baud rate is 9600 bits per second, though there are a pile of standard baud rates like 1200, 2400, 4800, 19,200, 38,400, 57,600, and 115,200. Now, faster is not always better. While it's typically true that you want to transfer as much information as possible, as fast as possible, you'll recall from Module 1, where if you run electricity through a wire, it generates a magnetic field around that wire. A wire in a moving magnetic field also gets a current induced in the wire. So pulsing ones and zeros down a wire is AC, isn't it? So the faster you pulse that line with data with a higher baud rate, that's a higher frequency of AC, isn't it? And the longer your communication wires are, the longer those wires are exposed to various electromagnetic waves, especially coming from one wire, the wire you're transmitting over, which is running right alongside your reference wire. There's more inductance at higher baud rates, fighting your signals getting across the wires, etc. So just bear that in mind when trying to run higher baud rates. Because we are running asynchronous mode, the next thing you'll need to do is you got to somehow get the two sides synchronized. Now, there is no common clock. You do this by throwing a few extra bits on the line, which set the timing. It's almost like providing a couple of clock pulses on the data line, then switching to data pulses. So these clock pulses can be 2 to 3 bits and are called the start and stop bits. You probably guessed they start the transmission of the byte and mark where it stops. The start and stop bits are not really bits, but rather time equivalent to 1 or 2 bits. When the line is idle, it is held high. So when the communication starts, the line level drops to a low or a 0. It stays low for the length of 1 bit. This is the start bit. Once the 8 bits have been communicated, the line stays low for either the length of 1 or 2 bits, then the line goes high again and idles in a high state. Because we've already predetermined the baud rate, we know what frequency to expect the pulses. So once that start bit comes in, the receiver zeroes its onboard clock, which has been set to the precise frequency of the communication. When its timing clock goes high, the receiver reads the line. If it's low, then it reads it as a 0. If it's a high, then it's a 1. It funnels the bits into a register on board, which builds the bits into a byte. The receiver knows how many bits it's reading, so it'll then watch its clock and the agreed upon time for the stop bits. It'll stay low the length of 1 or 2 bits, depending on how you set it up. Then the line goes high at idle, and the receiver sits there and monitors, waiting for the line to go low again with a start bit. Now, the most important thing here, again, is just that you know what the settings are, how the data will be communicated. Now, the most common default is 1 start bit, for obvious reasons, and 1 stop bit. Now, noise can get induced on the line. Someone turns on a nearby light switch, and an electromagnetic spike is reflected on the line just when the receiver was reading the line. So what was supposed to be a 0 got read as a 1 instead. So we might want to do some error checking. Parity is a very simple and fast form of error checking, and it comes in 2 primary flavors: even parity and odd parity. The parity is transmitted as a part of the data packet and is called a parity bit. So parity only has one of 2 results, a 1 or a 0. We have to be able to check out all 8 bits of our byte for accuracy using a simple math formula that gives either a 1 or a 0 result. Parity simply counts the number of zeros in the byte transmitted. Let's say it was 0110, 1100. We have 4 zeros, which is an even number. So now if we use even parity, because we have an even number of zeros, our parity bit will be 1 or true. If the number we transmitted had an odd number of zeros, like 0010, 1100, that's 5 zeros, so it's an odd number. So it's not an even number. So even parity would be false or a 0. If we were using odd parity, then the parity bit would be a 1 or true when there was an odd number of zeros, and a 0 or false when there was an even number of zeros. Now, I hope that makes sense. There are another 2 types of parity, mark and space, which in 30 years, I have never once seen these used. I simply mention them so you know they are there. The most common form of parity checking is none. That is, there is no parity checking and no parity bit. The reason for this is because the parity checking takes time. And when you're communicating over a serial connection, you're trying to save as much time as possible. Now, in such cases, there simply is no parity bit. But I'll show you the sequence of bits here with this drawing in a typical byte with a start bit, 8 data bits, a parity bit, and 2 stop bits. Now, obviously, you have the options of no parity, which would remove that bit, and 1 or 2 stop bits, which would remove that 1 bit if you so choose. You actually have the option of how many data bits you want to send as well, and that number will be between 5 and 9. Obviously, the default is 8 for 1 byte. The most important thing to take away from this is not what each bit does, but rather that both the sender and receiver have exactly the same settings, no matter what those settings are. Now, the most common default settings are 1 start bit, 1 stop bit, 8 data bits, no parity, and 9600 baud. Notice that 1 byte requires 10 bits total to transmit. So at 9600 bits per second, 10 bits per byte, that's 960 bytes per second you're transmitting. Now we take a look at a common and very useful tool which is available on probably every single microcontroller or computer you will ever use, the Universal Asynchronous Receiver Transmitter. We call it the UART for short. Your PIC has a UART, but also has a USB, the Universal Serial Bus electronics. The Arduino also has a UART, and you can use the UART to communicate between Arduinos or any electronic device that has a UART. And believe me, that's about as common as you're going to get. There was a few guys at DEF CON 23. DEF CON is the annual hackers convention, and they were hacking everything through its UART serial pins. Thermostats, TVs, network routers, digital cameras, security cameras, baby monitors, even refrigerators. In fact, just to make a point that low-level hackers could do this, they used common, off-the-shelf Arduino hardware to do their hacking. They just cracked open the device and looked for the telltale TX and RX connectors on the circuit board. And they then assumed default UART communication, and they were almost always right. So that brings me to the last thing. On your Arduino, you'll see it silkscreened right on the board, the TX and RX connections. This is transmit and receive. Now, if you're hooking up two Arduinos, for example, then you need to crisscross the wires here. Transmission is output, receiving is input, right? So if you hook up transmit to transmit, what do you get? Nothing. They're both talking to each other and not listening to each other. You need to connect the transmitter to the receiver on the other end and the transmit on the other end to the receive on this end. This allows asynchronous serial communication between your boards or between your Arduino and another digital device with a UART. There are other forms of serial communication like I2C and SPI, which we'll get into in more detail in later lessons and bonus lessons. But the UART is one of the most important ones. The one we're going to use the most is actually the USB connection that's built into your board. It is a serial connection between your Arduino and your computer, and we can actually communicate with the computer while the Arduino is running. In fact, you can now easily use the Arduino to interface your very powerful desktop computer to the outside world. One of the workshops I'm developing is computer-controlled rail traffic control system for model railroads. So using a desktop computer, interface to the model train set layout through an Arduino, we will control the trains, the switches for switching tracks, know where the trains are on the track, and control all the railroad signals. So serial communication can be very powerful and surprisingly easy to accomplish. In fact, we're going to use it in the next lesson.